All right, so in section 3.4, we're going to talk about measures of position. So we're going to talk about how a data point might relate to the rest of the data. So to do that, we're going to first talk about Z-scores. And the Z-score represents the distance that a data value is from the mean in terms of the number of standard deviations. And so we find it by taking that data point, subtracting the mean, and then dividing by the standard deviation. There's both a population Z-score and a sample Z-score, but really the only difference is that we are using mu and sigma whenever we're dealing with the population, so hopefully that makes sense. We'd have the data point minus the mean of the population divided by the standard deviation of that population. And then the sample Z-score, we're taking the data point, so that x, and we're subtracting the sample mean and then dividing by the sample standard deviation. And so it's pointing out here that the Z-score is unitless and it has a mean of 0 and a standard deviation of 1. So whenever we're looking at our Z-scores, we're going to go ahead and think about a nice little bell-shaped curve. And our mean, oops, let me try that a little bit better. There we go. So if that's our mean, then that means that our Z-score is going to be 0. And so if a data point is larger than the mean, we're going to end up with a positive Z-score, and if it's smaller, we're going to end up with a negative Z-score. And so the reason for using Z-scores, this is going to allow us to compare different sets of data to each other. So for instance, on our first example, we're going to look and determine who's taller between a man and a woman. Well, obviously, the average height for men is different than the average height for women, and it's also going to have a different standard deviation. But if we want to figure out who's relatively taller, we need to be able to bring this to the same scale somehow. So some way that we can compare, and Z-scores are going to be the way that we can do that. So the average 20 to 29-year-old man is 69.6 inches tall with a standard deviation of 3 inches, while the average 20 to 29-year-old woman is 64.1 inches tall with a standard deviation of 3.8 inches. Who is relatively taller, a 67-inch man or a 62-inch woman? All right, so let's go through. We're going to calculate these Z-scores. But first, I do want to point out, so we have a 67-inch man whenever the average man is 69.6 inches, and a 62-inch woman whenever the average woman is 64.1 inches tall. So both of these people are shorter than average. So we should be expecting a negative Z-score. So the Z-score for the men, we're going to take the data points, that's 67 inches, subtract that 69.6, and then we're going to divide by the standard deviation of that, which is 3. And let's see what that's going to give us right quick. So we've got the 67 minus that 69.6, and then dividing by 3. And let's convert that to a decimal by hitting the SD button. We're going to get negative 0.86 repeating. So negative 0.86 repeating. We want to go out 2 decimal places. So I'm going to write this out 3 decimal places so we can round. So 866. And then that 6 is going to bump this one up. So our Z-score for the men is going to be a negative 0.87. So there's one of our important numbers. So I'm just going to quickly draw our bell curve. And the mean will be right here, and that's going to be a Z-score of 0. And in men, we have a negative 0.87. So I'll just throw it over here somewhere. And we will say that this is going to be the negative 0.87. So the Z-score for the men. All right, now let's go through and do the same process for the women. So the Z-score for the women, we're going to take the data point of 62 inches. We're going to subtract the average for the women, so this is 64.1. Then divide by that 3.8. And let's work that out right quick. So we've got the 62. We're going to subtract the 64.1. And then divide by that 3.8. And let's convert that to a decimal. So going out 2 decimal places, we're going to have negative 0.55. So this repeating line here means that all of this is repeating. But since we're only going out 2 decimal places, we can just look at these first 3. So negative 0.55. So our z-score for the women is going to be right around here. So we got negative z-scores for both of those, which we were expecting. It's asking us which is relatively taller. So who's going to be relatively taller? Well, the women are closer to the mean because these are both short people. Then the women are going to be closer to average. The other way to think about it is that the women are above the men, so more to the right. So they have a larger z-score. Because we're looking for taller, then the women are going to be taller than the men, or this particular woman. So the 62-inch woman is going to be relatively taller. All right, let's talk about school admissions. A highly selective boarding school will only admit students who place at least 1.5 standard deviations above the mean on a standardized test that has a mean of 200 and a standard deviation of 26. What's the minimum score that an applicant must make on the test to be accepted? All right, so it's giving us that we need to have a z-score of 1.5. We're going to have the mean of 200 and a standard deviation of 26. So the z-score is the data point minus the mean over the standard deviation. So if we know that we have a z of 1.5, then we have the 1.5 for our z-score equals the data point's what we're after. So that's going to be our x. We're going to subtract that 200 and then divide by the standard deviation of 26. So now for us to go through and solve this, we would multiply both sides by 26 or cross multiply, whichever way you happen to think about it. So we're going to multiply both sides by 26. And the reason for that is that allows these to cancel. So then we have 26 times 1.5. So that's going to give us 39 equals x minus 200. So to solve for x, we're just going to add 200 to both sides. And we're going to end up that 239 is our x. So 239 is going to be 1.5 standard deviations above the mean on a standardized test. So that's going to be the cutoff score. Students are going to need to score at least 239 on this test. If we wanted to look at that in picture form, so here we have a z-score of 0 because that's at the mean, and we're looking for 1.5, so a z-score of 1.5. Well, translating that, so the mean test score was 200, and then the test score that corresponds to 1.5 standard deviations above is 239. And we're looking for all the people that are here or above. All right, let's talk about percentile. So the kth percentile, denoted p sub k, is a set of data with a value such that k% of the observations are less than or equal to the value. So if you score in the 97th percentile, that means that 97% of people had your score or below. So only 3% were above you. And we would have denoted that you were in the 97th percentile, like so. So whenever we have this p and then the little sub number, the little k, that's denoting everyone to the left of you. So everyone to the left of the score, to the left of the number. So let's look at an example. So we're going to talk about percentiles. The 15th percentile of the head circumference of males 3 to 5 months old is 41.0 centimeters. So the 15th percentile, so this is saying for A that 15% of males between 3 and 5 months old have a head circumference of 41.0 centimeters or less. And then for B, the 90th percentile of the waist circumference of females 2 years of age is 52.7 centimeters. So for B, we know that 90% of 2-year-old females have a waist circumference of 52.7 centimeters or less. All right, let's talk about quartiles. So quartiles, think of quarters, hopefully. If you're thinking of quarters, you hopefully realize that we're talking about fourths. So we're taking the data and we're splitting it up into 4 even pieces. And we're going to have Q1, Q2, and Q3. So we only need these 3 numbers to split data into 4 sections. So the first thing we're going to do is arrange the data in descending order, and then we're going to find the median. So this is just like what we talked about with the measures of central tendency, and we were finding the median. So we had to put all the information in order and then find the middle piece of data or the average of the 2 middle pieces of data if there was an even number pieces of data to begin with. So that's going to find our Q2. So the first number we're looking for that we're going to find is that Q2. And then we split the data into 2 pieces at that point. Once we split the data into 2 pieces, we're going to look at each half separately and find the median of each half. And that's going to give us Q1 for the lower half and Q3 for the upper half. So we're going to look here at number 21. For our example, the following data represent the number of inches of rain in Chicago, Illinois during the month of April for 20 randomly selected years. And we're going to find the quartiles. So we first need to know how many pieces of data we have. It said for 20. So to find our median, we need to go and find the middle of the data, and we're going to have to average the 2 middle pieces of data because we have 20, so an even number pieces of data to begin with. All right, so I believe right here is going to be about where our median's falling. All right, so here are our 10th and 11th pieces of data. So the median is going to actually fall right in the middle. And so we need to find the average or the mean of these 2 numbers. So for Q2, because again, the median is is Q2. We're going to do that 3.97 plus 4 all over 2. So we've got 7.97 over 2, which is going to give us 3.985. So this is going to be at 3.985 for Q2. All right, so now we've split the top set of data into 10 pieces of data and the bottom into 10 pieces of data. So now we're going to find the median of each of these. So here is our Q2. And now let's go through and find the median for the top 10. So that means we're going to look for the 5th and 6th pieces of data. So the fifth and sixth pieces of data, and we're going to average those. We're going to find the mean of those, and this will end up being our Q1. And so we're just going to do the 2.47 plus the 2.78. Then we're going to divide that by 2, because we're just finding the average again. And that's going to give us 2.625. And now let's do the same thing for the bottom half of data. And again, there's 10 data points here, 10 pieces of data. So we're going to look for the fifth and sixth of this. So it's going to be these two. And we're going to find Q3. And again, we're just going to take the mean, or find the average of those. So the 5.22 plus the 5.5. And then divide by 2. It's going to give us 5.36. So now we've got our Q1, Q2, and Q3. And then for this next part, it's asking us if we change this 7.69 to 15, is this going to affect anything? So again, if we replace that 7.69 with a 15, because we are only concerned in evenly dividing the number of pieces of data between these four quartiles, changing the last number doesn't impact anything. And actually, as long as this number had fallen within any of the last quartile, it would not have impacted our Q1, Q2, or Q3 because the data would have remained in the same order. All right, let's talk about quartiles a little bit more. So we just went through and found Q1, Q2, and Q3, but we had an even number of data points. Well, sometimes we're going to have an odd number of data points. So here we've gone through with the same example with the April showers, but instead of having 20 randomly selected years, we're going to have 19. So we've removed that last data point. So since we have 19, we're looking for the 10th data point to be our median. So our 10th data point is going to be right here. So this is our Q2. Now what's interesting here is that we have an odd number of data points. So do we include the median or do we not include the median into the top half and the bottom half of the data? Well, there's two ways to do it. You've got inclusive and exclusive ways to do this. So inclusively, you're going to be including that data point. So we'll include the median for inclusive whenever we're finding our Q1 and Q3. So we're going to look at these 10 data points to find our Q1. So we've got 10 data points, which means we're going to need to find the mean of data points 5 and 6. So we're going to find the mean of these two. So we've got that 2.47 plus 2.78. Divide that by 2. And we're going to get that 2.625 again. And so that's our Q1. And then again, because we're doing the inclusive way now, we're doing the inclusive method, we're going to include this median again. So we're including that data point again for the second half. So again, we have 10 data points. So we're looking for the 5th and 6th. So we're going to find the mean of these two data points. And we're at 4.995. And that's going to be our Q3. So again, this is if we are going through and being inclusive, meaning that we are including the Q2 or the median of all the data in the first half and the second half of the data to find Q1 and Q3. Now, exclusively, We are going to exclude the median whenever we're looking at the top half and the bottom half, or the first half and the second half of the data. So we're looking at these 9 points. Well, whenever we have 9 points, that means we're just looking for the middle data point, because this is odd. So we're going to look right here. And so that's our 5th data point. So that 2.47 is going to be our Q1 if we're doing things exclusively. And we'll look at the 9 data points of the second half. And again, the 5th, so we're going to go 1, 2, 3, 4, our 5th data point. So that 5.22 is going to be our Q3. All right, so again, inclusively, we're including the median so we're including our Q2 whenever we're looking at the top and the bottom halves of data to find Q1 and Q3. And exclusively, we are not including it. Now, I want to point out that we only have to be specific if we're going to do this inclusively or exclusively if we begin with an odd number of data points. So whenever we had all 20, it didn't matter. We would have all done this exactly the same way because a data point was not included in Q2. So if we had an even number of data points, it would have been the mean of 2 data points. Okay, let's talk about the IQR, or the interquartile range. So the interquartile range is the middle 50% of the observations in a data set. So it's where we've got 50% in the middle and then 25 on each end. So the IQR is the distance from there to there. So just like the range of a set of data is the highest number minus the lowest number, the interquartile range is going to be Q3 minus Q1. So again, we're back to our April showers with all 20 of our data points. And we had our Q1 and our Q3. So our Q1 was 2.625 and our Q3 was 5.36. So the IQR, we're just going to subtract. So we're going to have that 5.36 minus that 2.625. And our IQR is going to be 2.735. So what that means is that the middle 50% of the data are within 2.735, in this case inches, of each other. Okay, let's talk about outliers. So to find outliers, and so the outliers are going to be data points that are quite a bit beyond the rest of the data. So either too high, or too low. And those can be determined using the IQR. So we want to look for ones that are too low, and we would do that using the lower fence, which means that we're going to do the Q1, and we're going to subtract 1.5 of the interquartile range. So 1.5 times the IQR. And for the upper fence, so to find data points that would be outliers because they're too large, we're going to take Q3 and we're going to add 1.5 data points. So essentially, we end up drawing fences for our data. So we have our lower fence and our upper fence. Any data point falling beyond those is going to be an outlier. So again, with our April showers, we need to go through and determine our upper and lower fences. So our Q1 was 2.625. Our Q3 is 5.36. And then our IQR is 2.735. So to find the lower fence, we're going to take Q1 and subtract, so Q1 minus 1.5 of the inner quartile ranges, so the IQRs. So that's going to be that 2.625 minus 1.5 times that 2.735. And that's going to give us a negative 1.4775. All right, and to find our upper fence, we're going to take our Q3 and we're going to add 1.5 IQRs. So 1.5 times the inner quartile range. So that's going to be 5.36 plus 1.5 times that 2.735. And that's going to give us 9.4625. And now we're going to determine if there's any outliers. So if we have anything below this negative 1.4775, that's going to be an outlier. And if we have anything above the 9.4625, that's going to be an outlier. Well, we know for sure, because this is data about the inches of rain, that we do not have anything below negative 1.4775, because we're not going to have negative rain. For the upper fence, so determining outliers that may be too high, if we look at our highest data point, it's below this 9.4625 number. So in this set of data, there are no outliers. Okay, so for number 24, it's asking us to determine and interpret the quartiles, and then also we're going to go ahead and work through this and see if there's outliers. So, and it's asking specifically if this 6.81 is an outlier, so we're going to find out. So the first thing we want to do is determine the quartiles. Well, we have 26 pieces of data, so we're going to need to find the mean of the 13th and 14th piece. And the mean of these is going to be 2.165. And so now we've split this data into two halves with 13 pieces of data, top and bottom. So the 13 pieces of data on top, looking for our Q1, we'll be going for the 7th data point. So this 1.61 is going to be our Q1. So Q1 is the 1.61. And then our Q3, again, 7th data point. That's going to be our Q3. So we've now split our data into sets that are going to have 25% of the data in each, so into 4 parts or 4 quartiles. And we need to determine our IQR. So for part B, the inner quartile range, remember, is going to be Q3 minus Q1. So it's going to be that 2.68 minus that 1.61. So we're going to get an IQR of 1.07. And then we need to find our upper and lower fences. So our lower fence is going to be Q1 minus 1.5 of the IQRs. So 1.61, so that's our Q1 minus 1.5 times the inner quartile range of 1.07. So the 1.61 minus 1.5 times the 1.07. So that's going to give us a very small number. That's going to be 0.005 for our lower fence. And then for our upper fence, we're going to do Q3 plus 1.5 of the interquartile ranges. So that's 2.68 plus 1.5 times that 1.07. So 2.68 plus 1.5 times the 1.07. And that's going to give us 4.285. So that 4.285 is falling right here. So there's our upper fence, which means the 5.22 and the 6.81 are outliers. Our lower fence of 0.005 is going to fall up here. So the upper fence, there are no outliers. The lower fence so our lower fence, that 0.005, is going to fall up here. So we do not have any data points on the other side of that. So there's no outliers that are too low, but we do have two outliers that are too high. So yes, the observation of 6.81 is indeed an outlier.